Last time we were discussing initial value problem for the heat equation, and in this lecture we continue to do that. Okay. So recall, we are discussing this initial value problem. Last time we were discussing this initial value problem for the heat equation in the whole of Rn. So this was the equation we considered, and the fundamental solution of the heat equation or operator, also called heat kernel, this was defined by this expression, and using this fundamental solution, this Fourier-Poisson formula for the solution of heat equation was derived. Okay, and again recognize that this in the Fourier-Poisson formula, this solution U is defined as the convolution of the fundamental solution with initial data. Okay, and then we verify that this U given by the Poisson formula is indeed solution of the heat equation for T positive, and at T equal to 0 it satisfies the initial condition in this limiting sense. Okay, so that should be borne in mind. It's not that you directly put T equal to 0, because this K has a singularity at T equal to 0, so you have to interpret this initial condition in this limiting sense. Okay, so that's important, and in fact it's more local in the sense at wherever G is continuous, this limit holds true. Okay, so in particular if G is continuous everywhere, then this U given by the Poisson formula satisfies the initial condition in this limiting sense. In proving these two statements, we made use of some important properties of the heat kernel, the fundamental solution. So let me again state them for the reference. Okay, so for X belongs to Rn and T positive. Okay, so that's the only relevant region. For T less than or equal to 0, K is anyhow 0. So let's concentrate only for X in Rn and T positive, and for this, in this region, K is strictly positive because it's given by an exponential function. And if you look at the this exponential factor, say norm x square, so this is the standard norm in Rn. Okay. So K is symmetric with respect to X, and K is a C infinity function because we know that the exponential is a C infinity function, and this T, since we are restricting to T positive, so all these quantities are C infinity functions, so is their product. Okay, so C is a C infinity function, K is a C infinity function in this region, and that implies this function given by the Fourier-Poisson formula, that is namely the solution of the heat equation, is also a C infinity function for T positive. Okay, so bear this in mind, because we are assuming the initial condition only continuous and bounded, so that this integral is well defined. Okay, so for T positive, this U becomes a C infinity function, and that we call it smoothing effect coming from this heat curve. And in this region again, the fundamental solution satisfy the heat equation. More generally, we have this one. Okay, so we can take k as a function of x minus y here, and if you take this heat operator and differentiate with respect to x variables here and differentiate with respect to y variables, even that is 0. And this is another important property. So it's the total integral for Rn is 1. And this is another important property. So it's like uh, kind of averaging uh, any function we integrate with this as kernel. So this is an important property. So if you stay away from a positive distance from any point x, okay, so then this integral tends to 0 as t tends to 0. And this is used in this verification of initial condition in the limiting x. Okay, so this is again important. And as given by the Tikhonov example, in general there is no uniqueness, and for uniqueness we need to impose certain conditions on the solutions, and in one-dimensional case we have discussed this in detail, and same thing applies to even n dimension. So if you restrict, for example, the solution in the class of those functions with exponential growth, then there is uniqueness. Okay, and as I said here, so this k is a C infinity function, then u is a C infinity function, so that is referred to as smoothing effect. And this physically, this equation represents time irreversibility, in the sense, for example, suppose we are given uh, temperature in a rod uh, at time t equal to t0, we cannot say what was its temperature some time back. Okay, so that's referred to as time irreversibility. So only this heat equation, we can only predict what happens for future times, not backward time. Okay. Okay, this is the story of the heat equation in the entire domain. So we can ask now the question, what about bounded domains? Okay, and let's go back a little bit for the Laplace equation. Okay, so recall this Green's formula. So suppose omega is a bounded domain with smooth boundary. We require that smooth boundary so that the divergence theorem can be applied. Okay, so recall this Green's formula. So integral of any two functions u and v, we have this integral v Laplacian u minus u Laplacian v equal to dx equal to. So this is integral over the domain. So this is volume integral, and the right side is integral over del omega. So that's a boundary of omega. So that's a surface integral. Okay, and nu is the outward unit normal to del omega, and ds denotes the surface measure on del omega. Okay, now we apply this Green's formula to the following situation. We take u a harmonic function in omega and take v as the fundamental solution, call it phi. So this we discussed in the first part of this course, and also will be discussed a little bit even in the second part. So fundamental solution phi of the Laplacian, and then we derive this formula. So you apply here. So this is harmonic, so Laplacian u is 0, and this Laplacian phi is also 0, but there is some, as you know, this phi of x minus j, this has singularity. So if I consider that as a function of j for fixed x at j equal to x, so what we should do is we should uh, cut off a small ball around, so say epsilon. Okay, so first we should integrate over omega minus this ball, and then you let epsilon to 0, and that produces this u of x. Okay, so this we have done in detail in the first part of the course, and you can recall that. So we have a formula for the harmonic function in omega, ux equal to uj. So this is purely a boundary integral. These are called uh, single single and double layer potentials, and this should not be taken as formula for the solution, because this formula requires both u and its normal derivative on the boundary, and both cannot be given simultaneously. So this is not a formula for the solution, but nevertheless this is an important formula. We can use it for some other purposes. For example, here, so Laplace, if you use harmonic, means just Laplacian u equal to 0, and that requires only a C2 function, but this formula gives us that u is C infinity function. Okay. And this is because phi is a C infinity function. Okay, of course there is some singularity. Okay, but here if you look at this formula, j is on the boundary and x is in the interior, so this x does not cause any problem here. So this phi as a function of j is a C infinity function, and that's how we get u a C infinity function. Okay, and now we try to do a similar thing for the heat equation. Okay, and for that we introduce a new notation. We still call it k, there should not be any confusion. So now I write k is a function of 4 variables, x, t, y, a. Okay, x and y are in Rn, and t and a are R. Okay, so just so this is not this is just R. Okay, and we rewrite the Fourier-Poisson formula with this notation, and this as uxt is equal to kxtya uya dy, and this formula now gives, under appropriate conditions on uya etc. So this solves the heat equation for t bigger than a with the prescribed condition uxa on the line t equal to a. So earlier we had taken the initial condition on line t equal to 0, but we can take that initial condition on any line, okay, t equal to a. So this t equal to a, and you solve the heat equation here. So t bigger than. Okay, and this is the Poisson formula in that case. Okay, so now back again to so with this new notation. So let omega be a bounded domain with smooth boundary. Again, that smoothness for the purpose of using divergence theorem, and you take any interval, any finite interval on the real line, and you put, so q equal to omega cross AB. So this is a cylinder in Rn plus 1. Okay. So similar to the harmonic function, okay, so we derived here a formula for u of x in a domain, and here also we'd like to derive a formula for the solution of the heat equation at a point x in omega and t in this interval AB, given interval AB. Okay, and so those x and t, we hold them fixed, and now I consider this function as a function of xi and tau, and tau is restricted to this, tau is less than t. Okay, and then it's an easy verification that k satisfies this, what we call backward heat equation. Okay, and this plus, so there is a plus here, this is because of minus tau. Okay, so if you write this kx, okay, let me write that one here. So this is 4 pi t minus tau minus n by 2 into exponential minus x minus chi square, and I am differentiating with respect to tau, so there is minus tau here, so this is the one, and that makes this plus. Okay, so that's an easy verification, you can do that. Okay. And now let u be a solution of the heat equation. So I take that again as a function of xi and tau, u tau equal to Laplacian with respect to xi variables. So that is the stressing of the variables, and again we restrict to tau less than. Okay. And now you integrate similar to the Green's formula. Similar to the Green's formula. Now instead of only Laplacian, we will bring that heat operator. Okay. Okay. So I integrate from a to t, integral over omega k into u tau minus, so this is the, instead of Laplacian we have this heat operator, and here similar heat operator for v. So for ease of writing, I am just temporarily introducing this notation. V of xi tau is k of xt xi tau, because x and t are held fixed. Okay, and that, so if you take the first part, so this is v u tau plus u v tau, and that is same as d by d tau of u v, and the other part, so you have u Laplacian v minus v Laplacian u. So I have now omitted that xi variable, so but you should keep that in mind. So it's only with respect to xi. Okay, and this one now it's a uh, differentiation with respect to tau and also integration with respect to tau. So if just evaluation of this product uv at the end points, at this end point there is no trouble here. So this is just minus u xi a kx t xi a d xi. But at tau equal to t, this v is nothing but the fundamental solution. It has some singularity at tau equal to t. So that should be interpreted as you take the limit as tau tending to t from below of this function u xi tau and kxt xi tau d xi. Okay, so this valuation at t should be interpreted as taking limit as tau tends to t, because tau equal to t is a singularity for k. Okay, just look at here, there is a singularity. Okay, and now that's a good exercise in analysis. Okay, just show that this limit is precisely uxt. Okay, so this is for harmonic functions, if you recall. So for harmonic, so integral, you take a small interval around x, u xi phi x minus xi. Limit as epsilon tends to 0. So phi is the fundamental solution of the Laplacian is ux. Okay, so depending on what sign you choose, it could be minus, but it always gives you that. Okay, so in this similar fashion here, okay, so this fundamental solution acts in a similar way as the fundamental solution of the Laplacian and produces precisely u of xt. Okay, it is very similar to that, and it's a good exercise in analysis, and you should try that. And for this one, there is absolutely no difficulty, so we have just apply Green's formula, right? Green's formula, and convert this volume integral into this surface integral. Okay, and what is the left hand side? Left hand side, so you are assuming u is satisfy the heat equation, that is 0, and now just now we verified that this is also 0, so the left hand side is 0, and now this one gives you uxt, and you bring these two integrals on the other side, and we get this formula for the heat equation. And again, this is only a useful formula, but it should not be thought of as a formula for the solution of the heat equation, because this part is okay, this first part is okay, because this we are only giving the condition on the line t equal to a, so that's initial condition. But if you look at the boundary, it's demanding both the value of the function as well as its normal derivative, and we cannot prescribe both of them simultaneously. Okay, only one of them we can prescribe. So this is not a solution formula, but if you use a solution of the heat equation, you satisfies this formula. So in particular, we can use this again to show that so just like the uh, free variable case, that is the domain is whole of Rn. Okay. So we saw that u k is infinity implies u is infinity, and the same qualitative behavior continues to hold even for bounded domain. So if you use a solution of the heat equation in a bounded domain, automatically u is a C infinity function. Okay, so that's these such results are called regularity results, and both for the uh, harmonic functions and solutions of the heat equation, we see that they are uh, smooth functions, they are C infinity functions, and such is not the case with solution of the uh, wave equation, for example, that we'll see later. And with this thing, now we'll continue to study some more qualitative properties of the solutions of the heat equation. And the first thing we discuss is weak maximum and minimum principles. So this was again done for Kn equal to 1 in the first part of this course, and more or less the same proof continues to hold. There is absolutely no difference. Okay, so again omega is a bounded domain with smooth boundary, and we take some fixed t positive and consider this cylinder. Okay, so this is cylinder. So its base is omega and height is this t. And with respect to the heat equation, so there is some part of this boundary. So if you consider this closure of omega t, this is the one, and some part of this boundary is called parabolic boundary, and parabolic boundary is defined by this del p, p for parabolic, del p omega is omega t bar minus omega t. Okay, and in set theoretic notation, so you avoid this line t equal to t, that part, and you consider this part, and the bottom. Okay, you leave the top of the cylinder. Okay, so that you avoid, and you consider the other three sides of the cylinder, and that's called parabolic boundary. And the result is uh, okay, suppose u is a continuous function in omega t bar and having uh, this existence of u sub t and second derivatives, and they're all continuous in omega t, then the following statements hold. Okay, so if ut minus Laplacian u is less than or equal to 0 in omega t, and then the maximum of u in omega t bar is same as the maximum of u in on the parabolic boundary. And similarly, if ut minus Laplacian u is bigger than or equal to 0 in omega t, then the minimum of u in the whole omega t bar is same as minimum of u over the parabolic boundary. And if you satisfy the heat equation in omega t, then the maximum of mod u. Okay, so both, because then this will be equivalent to both less than or equal to 0 and bigger than or equal to 0. So both the maximum and the minimum of u in omega t bar are same as maximum and minimum over parabolic boundary, and that is stated as, so you can just take mod. Okay. So this mod u contains both maximum and minimum. Okay. Uh, so these are called weak maximum and minimum principles. So the importance of this statement is the maximum of u certainly occurs on the parabolic boundary, but it does not rule out the occurrence of maximum in the interior. Okay, that's why it is weak. The strong maximum principle concerns what happens if the maximum occurs at an interior point. If you compare this, for example, with harmonic functions, so harmonic functions also we saw that. Let me just write it somewhere here. So for harmonic functions, so if omega is connected, okay, so that's recall that. Then for u harmonic omega, and of course want to have continuity up to boundary, then if u is non-constant, its maximum can occur, why can occurs only on. So this is the strong maximum principle. So when omega is connected, uh, this uh, it if omega is connected, a harmonic function cannot have a maximum in the interior unless it's a constant function. Okay. So similar statements are true even uh, for the heat equation, but these are more technically involved and involve construction of special solutions, and that will avoid this first part. Okay, so and the proof of this theorem is very simple. So it's just follows from taking this auxiliary function, and even let me remark, so it suffices to prove the first part. For the second part follows if you replace u by minus u, and third part follows if we replace take u and minus u both. Okay, so suffices to prove 1. Okay, and for that you consider this auxiliary function, and you see that this is less than 0. Okay, so now assume v, okay, v takes its maximum at x0 t0, where x0 is in omega and t0 we want to rule out even and t, but suppose we take that. Okay, then this v sub t is always either 0 or it can only be positive. 0 if t0 is strictly less than t and vt bigger than equal to 0. Okay, and since this is an interior point, okay, so we get this vi xi are all 0, and the Hessian, okay, let me just write that Laplacian p at x0 t0, since it's a maximum, okay, just we're assuming it's a maximum, so this is less than equal. So therefore Vt minus Laplacian p at x0 t0 bigger than, and this is a contradiction to this statement. This is a contradiction. So we cannot assume maximum in the interior. Okay, so therefore we assumes its maximum only on. Okay, so to conclude the proof, just you see that. So we have put v is equal to u plus epsilon norm x square. Okay, so we have v less than or equal to u, and this is of course v this just a minute. We have v is equal to u plus epsilon square. So u is always less than or equal to, and this is less than or equal to u plus some epsilon, let me call it. So m is the maximum of mod x square x in omega. And from this we can easily conclude that. Okay. I stop here and we'll continue from this next time.